All right, welcome everybody to our fourth week of image segmentation of our micro course, where we'll be going through image segmentation using deep learning. This is going to be more fun in a way, although it looks very complex and all, but frankly, it's just a bunch of clicks and you can go ahead in your life with what you need in terms of your final data set. And some of the images that we will generate from today, we will be using that next week in Cell Profiler, okay? So again, who are we? We are a team of biologists and physicists who are here to help you with any stage of your microscopy. We help you with supporting any of your designs of microscopy experiments. We consult with you. We educate you in terms of data analysis, as well as image acquisition, as well as training on any of the microscopes that we have at Emory. So as always, the consultations are free, and we have 19 different microscopes that can help you with any of your tasks. Once again, you can visit the website either@emory.edu or join us on our Slack channel and few of the things which you are familiar with by now. It's okay if you don't use Slack channel, but please give us feedback. Let us know if you have any questions. And we are a very small group of people today, so let the questions flowing. Okay. So some of the outcomes that I envision for today's session is something you will be really good with using StarDist on Fiji. Again, the goal is not to scare you with programming if you are not familiar with that. The goal is to use straightforward methods which can take you from point A to point B without putting any or much effort in the process, right? So there are different ways of using StarDist. One is using either Google Colab or even Python, but we will be using StarDist, which integrates with Fiji, which I think everybody is okay with now. What it can do and what cannot do, I'll talk later, but briefly, you can only use 2D images if you are trying to use StarDist on Fiji, whereas if you are trying to train a model by yourself, then you can use Google Colab, zero-cost deep learning notebook. Or if you want to do some kind of 3D-based image segmentation, then you can go and run the StarDist code using Python, all right? So if any one of you are interested towards 3D-based segmentation, do reach out to us. We have got different tools. We can help you with that. Apart from that, we will be using Cellpose, which is very bare minimum way of doing this. And again, the executable file that I propose to you for using will take you from step A to step B that you see over here. The beauty of that is that it gives you the data sets, even if your staining is really terrible in the background. And all of this depends on the model or the cells that they have used to generate a data and a model from that, okay? And I forgot to mention that this data set was given to us by Dr. Nikita Gupta's lab, so thanks to her for that. Okay, first thing first, which is, you know, all these words, jargons people keep on throwing around: artificial intelligence, machine learning, deep learning. What are they, right? So artificial intelligence can be easily defined as any kind of a program or a network in which allows us to do any task that human can do, right? So it's easy to say that, oh, it's an AI thing, but one has to train it. And under the broad umbrella of AI falls something called machine learning, all right? Now, machine learning is an algorithm which improves the task that one is doing over the time. The more data that you feed into the algorithm, the better it keeps on getting. It uses various statistics to create a bunch of models from the observed data, right? So again, The more data that you have, the better the model gets. And it also uses a bunch of human-derived classifiers, which helps in feature extraction process. Now, going even deeper into machine learning. So deep learning is a subset of machine learning, which automates some of this human-derived classifiers, which are called the feature extractors. Right now, you can use this feature extractors to train some complex neural networks, right? So this is where deep learning really uses a bunch of models called convolutional neural networks, or CNN. And that's where the word neural comes into picture, which is it kind of tries to resemble the neurons of our brain. And these neurons are nothing else but a bunch of feature extractors, which tries to decide what a particular task is or a particular feature is, okay? But the only drawback of deep learning is that it requires a lot of computational power. It requires a ton of GPU, and hence a lot of tasks that we are doing, or some of the software that we are using today, does not require you to use GPU. If you were to train a model of your own, then yes, you will require a lot of GPU power. Next year, when we do the second iteration of this course, we want to go into tasks, for example, using Google Colab-based notebooks, where you can use GPU in the cloud. So even if you do not have a massive amount of GPU power to train a model, you can use cloud-based resources to train your own model, and then import that model into Fiji and utilize to essentially do what we are doing today, okay? So everything we are doing today is very generalist, based on the cells and the nuclei that people have trained and the models that were generated based on existing data. If you have a very unique data set that does not work really well with the models that people have trained, and that you will be using with either StarDist or Cellpose, at that point, training your own model really helps you. So what does all of this mean, right? So how do you train a model? What essentially it means is you have to annotate your data, right? So you have over here something called the training data. That's the data which you want to use to train your model. Now, before you use your training data, you have to annotate that. What that means is you have to draw segments manually to let the model know what feature of importance that you want to highlight. So for example, if you want to highlight the entire nuclei, you literally segment or annotate the nuclei. If you want to highlight the mitochondria or actin, you draw labels on that to highlight those relevant features of your data set. That gets into a model, which is your convolutional neural network. And there are two different features of the model, the weight and the bias. And this is something which is very much tunable, right? So you feed into the model, and you don't have to start all these things from scratch. There are a bunch of models which are available, which you can tweak and try to get something which best fits your need, okay? So from that, you will get an output, and then you use your test data to see if this model is working or not. If it's not working, you go in and tweak this weights and biases till you get a satisfactory data. Now, when I say satisfactory data, it's not simply about me looking at it and saying, okay, I'm happy with it, right? There has to be a way of figuring out whether it's satisfactory or not. But before that, I want to talk a bit about some of the most commonly used deep learning model specifically for the biological images. Now, specifically for the biological images, UNet is a commonly used deep learning model. And UNet is one of the convolutional neural network-based model, right? So this is what fits right over here, okay? And what you see on the left side is an input image tile, which undergoes a process of dimension reduction, right? So this is also called an encoder. And as you go towards the right-hand side, it undergoes a process of a decoder event, which is also an increase in the dimension. Now, during each of these processes of dimension reduction and an increase in dimension, you can adjust the weights and biases, which is what the thing is over here. And all of this gets into linear regression and whatnot, and that's not the goal of this workshop today. However, in lecture number 7, where we have Dr. Srinivas Bhattiprolu, he is a guru of all these things, and he's going to talk more about all these processes. So if you are interested in knowing the technicalities of how the deep learning models work and what it does, he's going to get into the nitty-gritties of all of this. So I highly recommend participating in his lecture. It's going to be really fun. Okay, so once we go back over here, which is we have some kind of data coming out, right? How do we know how good our model is performing? So in order to know how good the model is performing, there is something called intersection of union. And this intersection of union is based on the area of overlap over area of union, which is again based on precision and recall. And all of this deep learning adventure in the field of biology started with the data ball, which was sponsored by the group of Ann Carpenter up at Broad Institute. And this is what they essentially published in the competition when people participated. One of the person who got the top score, they use a UNet model, and the other people, for example, the Jacobi group and the Deep Retina group, they use a convolutional neural network model. However, what was realized in this competition is that these models are not amenable for people to use routinely because they don't have crazy computational power. And within this few years, 2018 till now, in 3 years, a lot of groups have come up with models which let you use them in a very efficient manner without a lot of GPU power. And that's something that we will be using today, for example, StarDist as well as Cellpose, right? So StarDist and Cellpose really came after this paper was published, all right? So few definitions that you should be familiar with. Something called instance versus semantic segmentation, where people talk about in this field. So for example, in instance segmentation, you can classify everything as one group and say, you know what, I can see people in general, but who are these people? When we start classification of people as unique individuals and assign them label, that is essentially semantic segmentation. So with all the, for example, with StarDist, the output we get are individual objects, and we have a region of interest per individual object, right? And that is something which we will call as a semantic segmentation, okay? So moving on to StarDist. So StarDist is a model which is based on UNet. It has been not, the paper says it does not work best on images with low signal to noise ratio. I haven't had a terrible image, I guess. So pretty much most of the images that I have tried, the StarDist model has worked pretty good. The model predicts the state, a shape representation, essentially a star convex polygon, which is how most of the nuclei are, right? So they typically have some kind of a polygonal shape, which defines the nuclei. It inputs all of those values into this UNet-like model and generates this score, which you can use to identify how many nuclei you have, right? So unlike what we have used before, which is threshold-based method, you are not doing any kind of thresholding. It's based on this complex math that they have figured out earlier. And you are simply using this model to know whether the objects that you have fit into the model that somebody has made, and you can get going with this. So you cannot use StarDist because it's based on complex convex polygons. You cannot use this to detect shapes which could be which could not be fitting in this polygonal criteria. So if you have a shape with protrusions like filopodia and so on, StarDist cannot work really well on that. Okay. All right. So jumping directly into the exercise, the goal is to compare segmentations between thresholding-based method and StarDist, right? So I want you to appreciate the differences between how a model like StarDist will give you data versus a model like thresholding-based method will give you data. Now, last time when we were doing thresholding-based methods, the nucleus that you were working on was straightforward. It was from 2D data set. But what if you have nucleus from models such as in vivo data set, right? So this is from lungs. And what you can see is when you get into in vivo data sets, the nuclei are touching, they are dense, they are touching each other. They have got different features. They've got all of these dots. Some of the nuclei are even very different than this. And that's something which is part of the liver data set. So the first exercise that I want you all to do is to open this crop.tiff file from the lung nuclei folder and try to segment it based on the thresholding based method, okay? And following that, apply the watershed feature or algorithm to segment or make sure that the touching nuclei are no longer touching each other, okay? So let's get going with that. Even I will do that along with you and see what we got, okay? So again, just to remind you, Shift Control T for thresholding, and if you are using Mac, it's Shift Command T. So this is something that you get when you are segmenting, and typically I would go to default, but for consistency purposes, I will just use the Otsu method of thresholding. And I'm going to hit apply to that. You know, this is what we get, and everything is just connected. So one of the straightforward thing to do is go ahead, go to process binary and apply watershed algorithm, and we get individual nuclei, right? So straightforward, simple. How does everybody feel about that? Oh, awesome. Okay, so once you are here, I will keep this window open. The goal is to compare how things are faring. But one thing you can do to see how good or bad this is overlay this onto your original file, right? So let me open my crop.tiff again. Let's go to image, color, merge channels. So let's merge both of these channels. And before I do that, Let me convert this to an 8-bit image so that, okay. So let me go back to image colors, merge channel. I will be merging my crop and crop1.diff. Okay, and you can clearly see that whatever is green is my original data. Some of the nuclei do not match up very well with the original data, right? Because we are at the mercy of how much we are thresholding. And some of these regions, for example, let's see if I play with this, play with the original data. Some of these nuclei are individual, for example, right here. And if I try to annotate this, so for example, right over here, these are 1 and 2 nuclei. However, if I look at my images, this one appears as 1, right? So there are lots and lots of some of these examples where it just appears as one object versus multiple objects. So in an example for, let's say, something like this, where you have data from tissues, right? And I want to segment individual nuclei, I could be grossly misrepresenting as to how many nuclei I have, where I have almost tens of thousands of nuclei present over here, right? So we need a way to precisely say how many nuclei are present over here. And that's where StarDist really comes handy. All right, so let's jump onto StarDist and talk a bit more about that. So once you open the image and you go and launch StarDist, you see a window which looks like this, right? And I'll talk a bit about different models that they have. But two key regions that you need to think about is what kind of values you want to apply for your probability score threshold and your overlap threshold. If you increase this, i.e. go towards right, what it means is you are detecting fewer objects. And if you go towards left, which is reduce this probability score threshold, now you are selecting for more objects, even if they are overlapping or so, okay? Versus if you are looking for counting individual objects, if you move towards right, where you are looking at the overlap threshold, the same object gets counted multiple times, okay? So if you put the overlap threshold to, let's say, for example, 1, the same object will be getting counted repeatedly. So that's something which you can play with later on today. So the first thing is to segment nuclei using StarDist. And it's straightforward. You open the image, you go to the StarDist 2D plugin, you apply certain values to it, and I will let you play with these values so that you understand. And again, these are way too many nuclei, so you probably won't be able to know how bad it's going when you are going with this value. And that's where using one of the 2D data sets with fewer nuclei will be very helpful. So that's something which we'll be doing later on. But with this data set, if you play with the probability score threshold, it will become very clear what's going on, okay? So, and once you apply okay, you will get a lot of these values, which are part of the ROI manager. You can enable both show all as well as labels onto the nuclei and see how many cells you have, right? So here, it will be very much clear whether you have selected for an individual nuclei or not, because if things are overlapping, it should be obvious based off of these labels that things are very much messed up. And then well, let's just hold on to the next step. So let's reach to this tab, and then we will go on to creating masks from here. Okay, so I'll go ahead and open. I have my image open right over here. I'll go to plugins, Stardust 2D, and it brings up this window. And I'll just keep my probability score threshold and overlap threshold at 0.6 and 0.7 and see what I get. Okay, so I do that, and I get some nice colorful ROIs, and this is what I get on my ROI manager. And if I click on my crop one image and click on show all and labels, it has done a decent job. But if I want to make sure it is okay, I can go in, and here you can see that there are a bunch of this overlaps which should not be happening, right? So for example, this 278, I'm not too happy with it. I'm not too thrilled with some of this objects that it's showing to me. So what I'll do is let's try and repeat this. And this time I will, let's say, go to plugins, StarDist 2D, and try to reduce, or sorry, try to increase my probability threshold score to, let's say, 0.75 and say, okay, all right. And you can see that it has reduced some of the objects that we were getting previously. And I should have, let me redo this because I did not remove my ROI manager before. So let me go back and redo this. StarDist 2D. Say okay. So this, and now if I go to my ROI manager, show all labels, right? So now it looks a bit more satisfactory. All those weird overlapping objects that I was getting, for example, over here, I'm not getting. But at the same time, I'm also losing some of the cells, which I think I should be getting, right? So this is where you have to play between this values and see what works best for you, okay? So I'll let you play with this and come to a satisfactory point, which is sort of a happy medium for you, okay? So play with it, come to a happy medium. But one more thing, the models, right? So why are we using just the versatile fluorescent nuclei model? It's the most popular model. You can also use the data science ball model from 2018 and versatile H&E nuclei. If you are having any H&E data set, you can use that at that time, all right? So you can either use the versatile fluorescent nuclei model or the data science ball 2018 model that is from the StarDist 2D paper, and see what your data looks like. And you can change these values to get to something which is the happy medium that you are happy with, okay? So I'll let you play with this for 5 minutes, and then we can reconvene back. And let us know if you have any questions. How's everybody doing? Any questions? We good to move to the next step, or? Yeah, good to go to the next step, guys. Or you want to need some more time? All right, thank you. Okay, so moving on, the next step is to create masks from ROIs. Now, typically what one would do at this stage is like, okay, you know what, I have got all this nuclei, and this is something that we looked at last time, right? So well, let me go back to my presentation and I'll talk a bit more about why you would do and what you won't do. Again, the goal for us is to utilize the segmented masks that we get today and kind of semi-automate this process by using this into cell profiler, okay? And then that's why we need this automated mask. For example, we will try to see if we use the same image in cell profiler, how good of a segmentation it can do, right? But if you want to use one of the deep learning models on cell profiler, which you cannot at the moment, this is one way of doing this, which is you generate a mask outside and you can import that mask into cell profiler. And then based off of that mask, you can generate either cytoplasmic mask and generate data based on the features that cell profiler gives to you, okay? So let's say the goal is to create masks from ROIs. We get all this ROIs. The first step you will do is to generate a new window, a blank new window, okay? And if this is the pixel dimensions of your current image, you will enter the same pixel dimensions in this new image window and say, okay. This will open up a new window with all black background, okay? And from there, you will go to ROI Manager, select all your ROIs by going on to, by selecting all of them. So Control and left click, that will help you select all the ROIs. Go click on More, then click on Fill. And once you click on Fill, that should give you all this cell masks, all right? However, the nuclear masks in this case. So one of the problem is clearly evident over here. And would anybody like to jump in and tell me what the problem is with this masks or the objects? And I should really, it's a bad cut copy paste job. It's a nucleus mask and not a cell mask. So what is the problem over here? There's a problem. What's the problem when I look at these objects? Anybody want to jump in?
There are not clear divisions between some of those objects.
Exactly, right? Thanks, Lucas. So there are no divisions between these objects. So if I was to try to quantify this in Cell Profiler, what's going to happen is all of this will be counted as one object, right? And that's not good. So the easiest thing we can do is, this is a binary image. So on that binary image, we can apply Watershed and boom, now we get individual objects that we can easily quantify, okay? So that's the goal for this exercise. So let's go ahead and do that part, all right? So I have all of my ROIs right here. And again, with this ROIs, we can do something that we did last time, which is go and measure them, right? So again, I'll go ahead and select the first ROI, control, click, or shift click. Did not select all of them. Go ahead and shift click, shift left click. And if I try to measure, it gives me all this fun values for each of my object, right? The area, raw integrated density, mean intensity, and so on. We don't care about the area and so on for this, but we still get values. But if you want to do some fancy things, for example, subtract this from the entire cell and just get data from the cytoplasm and so on, then we do need this masks, okay? So let's go back to what I was proposing before, which is Control and, which gives me a new window, and I'm going to input 654 by 636, say okay. And we don't see anything over here right now. But if you were to go and click this individually, you will see that there are a bunch of objects which are getting highlighted right over here. Again, do the same thing, which is shift and left click all my ROIs, go to more, fill. And once you fill, you will get all these objects. And the best part is these objects are binary, right? So background is black, that's 0. If you go on to objects, that's 255. So we get this nice binary objects. However, they're all touching with each other, and we want to segment them out. So we'll go back to process, binary, watershed, and boom, we got individual objects now. Okay, so it's that straightforward. Go ahead, give it a shot, and you can save this as nucleus dash mask. Okay. So I'll let you play with this for a few minutes. It's straightforward, kind of.
I have a question.
Yeah,
Because for some reason it doesn't allow me to do the watershed. It complains that the image is not 8-bit, but the image is 8-bit.
so what image are you doing watershed on?
The one that I produce out of the ROI manager.
Okay, so can you try this again? Most likely you might have clicked on the original image. So try clicking on your thresholded image once more, and then try doing it.
Okay, let's see. But I'll produce this new image, right? First.
Right.
Okay.
And if you want, I can let you share the screen so that you can show if that's a problem.
Let me see if yeah, no, it's still complaining.
Okay, can I?
Let me share the screen.
Yeah, please.
Okay, I guess you guys are seeing this screen here.
Right.
I'm going to
So
the bar from the Zoom doesn't allow me to to get to the image. There you go. I'm going to close this one, okay?
Okay.
And I'm going to generate the new one.
Okay, and then you can also close this ROI manager. Let's close the ROI manager too.
This guy? Okay.
Yeah, just close it.
So let's go like this. This is what I generate, right?
Yeah, 6.5. Yeah, perfect.
Okay.
Oh, but you will need your ROI manager. So you might have to go back and redo the StarDist thing on your crop.tiff again.
This guy?
Yeah, so let's run the StarDist again.
Where are you?
Scroll down.
This guy. All right. Okay. Okay. So let's say that we go like this. I think that was the original setting. This guy here. Okay.
Okay.
There we go.
Wonderful. And now let's enable show all and show labels to see how well it looks or not. So if you can minimize the label image, let's minimize your label image.
Which one? This one?
Yeah, if you could please minimize that image.
Well, because the toolbar from the Zoom does not allow me to.
Yeah, so with the Zoom toolbar, I think
it's very annoying.
Yeah, it's
there you go. There you go. I was able to move it. Okay, I can minimize this guy.
Okay, wonderful.
So now I go to.
Yeah, perfect. You are good.
Go to this image and I'll scroll all the way up here and all the way down here.
Perfect.
More fill.
Okay, so that's what you got. Can you do Control N? I want to see what kind of settings you have for
Control N.
Yeah. Okay. So 8 fill with black. Yeah, that looks everything looks fine. Okay, let's cancel that. Okay. And
so
let's
now if I go to a process binary watershed, this is the complaint that
I see, because say okay, because go and move your cursor onto one of your cell and also bring up your Fiji toolbar.
Yeah, I saw your.
This guy. Okay.
Yeah, because it's not a binary image, right? So if you put your cursor onto one of your nuclei, let's look at the values, right? So that's not a binary image. I don't know why. So let's make it a binary image.
Okay.
So just go ahead and geez. Let me see what options I have selected that it gives me binary right away, but not you. Is anybody else having this problem? So you can try to image. So it's sorry, go to process, binary, convert
Make
to
binary.
no convert to
Okay.
mask.
Okay.
No, that did not work out. Do Control Z. Okay. Do Shift Control T to
Give
get
me
a
a sec, please. To do with the voice. Of course. Thank you. Okay.
So let's
So
try to
now
bring up thresholding menu, and I'll see if there is something that you need to click to get a 8-bit binary image, which you are not getting. Does anybody else want to pitch in if you're having the same issue like this, like Lucas?
if I hit make binary, it doesn't work.
Give it a shot. No, it doesn't work.
No, it does not.
So I would try to do Shift Control T, bring up the thresholding menu at this point, and do auto. Just hit auto. Does it?
It doesn't do anything.
So move your top one towards left. The bar of it where it says 129 in the threshold.
129 to the left. Okay, it's this image.
Okay, and that's good. And apply. Okay, and it's inverted. So go back to your lookup table.
Which table?
LUT. Well, there is this small button next to stack and LUT on the Fiji bar. Yep, LUT and do invert LUT. Wonderful.
Oh, okay.
Okay, and now you can apply, go to process, binary, and do watershed.
Oh.
Okay.
Interesting.
Yeah, very interesting. Let me see why it's not giving you what you are supposed to get.
Sorry, I'm that guy today.
No, I think I need to figure that out, because I think everything that I'm using all the time repeatedly gives me the right thing. So what's giving me the wrong thing is what I'm interested in now. So let me try and see, okay?
Okay. Mm.
I'm really confused why you are not getting binary, bothering me a lot. Does everybody else get binary data when you apply this kind of a method?
I've similarly been having an issue where when I go through the thresholding step, my images are inverted from yours, but I've just been kind of going with that inverted image. I'm not sure if that is where the
Yeah,
issue
me
is
too.
coming up for you.
So what if you, so Lucas, where I asked you to invert the lookup table, what if you do not invert the lookup table, and on that, you go ahead and try to do a watershed function? Can you give that a shot and see what happens?
I am doing that now.
Okay.
Now it's still complaining about the picture not being an 8-bit binary image, which is a little bit ridiculous.
I mean, it does say it's 8-bit, but I don't know why your image is not binary. And Stern, does your image give you binary when you do this?
Yeah, I'm having trouble recreating the problem.
Yeah. I'm gonna try this on 2 other machines that I have access to, Lucas, tomorrow, and see how it turns up, and I'll get back to you on that.
Sounds good.
Yeah.
Thank you.
Yeah, you're welcome. But did the other function work for you where you tried to do watershed function on the inverted image?
From this image, no.
Okay.
I mean, I've been using the watershed function before with other images, but not for this one. It's not working. Interesting. Okay.
Okay, I guess while all of that is going on, we have 1 more hour. So let's kind of finish up this one last exercise. which is something which will help you figure out what overlap threshold really is, which is if you really have it at high, which is 1, what's going to happen with the number of objects that you are counting. So if we open up the file, which is in the 2D cells folder, which is 20x-cropped. And what I've done is for you guys to play whenever you want to, I've also included a bigger file, for example, 2D cells 20x diff, that's a larger file. In the interest of time, to make sure that things kind of keep on going fast and it's not memory intensive on your computers, I've essentially cropped a region on which we can work. But here's an entire file which has got lots and lots of cells. You have got the nuclei, the entire cell with actin, and the one in mitochondria, right? So if you want to play, you can crop any region that you want to, or select or duplicate any region that you want to. But I've already cropped one of the regions for you to play with. So I would like you to open the 2D-20x cropped file .diff. And this is what you get. And the goal is just to get the nucleus out of it. So I'm gonna use my first channel, say, okay, this is all I care about. And on this channel, right, we have got some nuclei which are bright, some nuclei which are dim. So I'll go ahead and again use my StarDist plugin. So the point I want to make is what happens. Let me close my ROI manager first. And if you have your ROI manager open, go ahead and close that. So the point is, let's say right now my overlap threshold is at 0.7, right? And what you see is I have got just the right number of cells. There is no over numbering going on. But if let me close, there are 53. Let me discard this. If I go ahead and plugins, StarDist, let's say bring the overlap threshold to 1 and say, okay. It looks kind of fine over here, but if you zoom in, what you will see is there are multiple colors over here, right? Which means the same nuclei is considered as an object multiple times. And if I look at my ROI manager and let's say show all labels, boom, we have what, like 400 of them. And we know we only have about 50 different nuclei, right? So this is something you need to be careful about when you are doing, when you are using StarDist, that you do not overinterpret the numbers. It's easy to miss on this if you do not read the documentation properly, okay? So just wanted to highlight this, and this is where playing with parameters that you have in this toolbox is kind of important, that you do not have highly overlapping parameters, okay? So go ahead and play with this. This was not very clear with a very complex data set as lung, but with a simple data set like 2D cells, this is much more clear, right? So go ahead and play with this. So if I, let's say, increase my probability threshold score to, let's say, 1 over here, I'll be most likely selecting for fewer. I did not get any nuclei, not even few, but didn't get any nuclei, right? So this data set will really help you to understand any of the tweaks that you can have with StarDist. Okay, so what I'll do is, in the interest of time, we have 45 minutes remaining. You kind of got the gist of this. I'll let you play with this at your own time, but I would like to move on so that I don't hold you up way after 6 o'clock. Okay, all right. So moving on to Cellpose. So Cellpose is really fun. I'm sorry for those for whom this did not work out. The kind of GUI interface did not work out. But what they have done, and this is from Carson Stringer's group up at Janelia, what they have done is they have used the segmented images, right? So you annotate the images which are right over here. You manually annotate the images. So that's the annotated mask of the image. You create this kind of topological maps through a process of simulated diffusion that uses the ground truth, right? So when somebody uses the word ground truth, it means the exact definition that somebody has generated onto an annotated region. So once you simulate this diffusion, you get this spatial gradient patterns, which results into generation of this kind of gradients, okay? And then this kind of annotated regions and these gradients are fed into the neural network to generate this horizontal and vertical gradients. What it also takes into account is the boundaries and the edges. As soon as it realizes that there is a pixel which is background compared to your actual signal, it's going to create a boundary right there to generate this sort of combined gradients, right? And then what you get finally is a mask, which is essentially your region of interest. So this group has utilized lots and lots of cells which were manually annotated and fed into the system. So based on this different shapes, anytime your image has any decent signal to noise ratio or a pixel which is bright and a pixel which is dark, the model will try to predict whether or not there is a cell present over there. Okay, so that's essentially what Cellpose is trying to do. And when we look at the performance of the model based on the average prediction versus the IOUs, Cellpose does a pretty good job compared to any of the existing models. You can use Cellpose for both for not just both, but for cell membrane. You can use that for an entire cell, and you can also use that for the nuclei within Cellpose now, or nuclei within the cells. So what we'll do in terms of exercise is segment images based on Cellpose. So you can go from something like this to getting something like this, okay? So let's go ahead and open our image, which is 2D cells dash crop. Now, one thing to remember for Cellpose is it does a great job only if you have both the nuclei and the cytoplasm. If you were to just have an image with cytoplasm by itself, Cellpose won't be doing a great job, okay? So always make sure that you have data sets with both nuclei as well as cytoplasm. Apart from it, in the folder that you have, you will find some files, which is Fiji files for Cellpose. This will come handy later on, okay? So let's go ahead and create a file which has got nucleus and cytoplasm. So I'm gonna drop my 2D cells -20x crop right over here. We have got 3 channels. I'm going to duplicate my file. Actually, you only have 2 channels. Never mind. I thought I had mitochondria in it, but you do not have mitochondria, so ignore what I said. You have 2 channels, okay? So this is good enough and perfect to be dragged and dropped onto Cellpose. So essentially what you will be doing is opening or launch Cellpose. If you are using PC, it's straightforward. You can double click on your cellpose.exe file. That will be straightforward. I'm using a Mac, so I'll go through all the hoops of launching it. So let me go back to the email and follow up on the instructions that I sent you earlier. So the first step I want to do is open my terminal. Should let me close everything since I already have opened Terminate. And an easier thing to do is just copy the commands if you don't want to type everything. But I'll just go ahead and type. So I'll change my directory to downloads. That's a news. Did something happen to my downloads all of a sudden? That's fantastic. So for some weird reason, my terminal would not recognize that I have a downloads folder on my computer, which is not fun, which is what I need for this entire demo. Okay, so I tried to go there manually. Hopefully this should work out. Let's see. I guess it's trying to work out. It's doing something. Or so I think. Okay. So I got my Cellpose window. Now, few things about this window. What you are seeing over here is in terms of brush size, which is how big the borders when you are drawing something is going to look like. So let's say you can draw. It's not popping up right now, but I guess once I load the image, it should happen. One of the straightforward thing to do is to go ahead and drag and drop this image onto Cellpose, all right? And it's generating the masks right away because I already have done something before. So let me remove this files from here so that it doesn't give me anything. Okay, but that's okay. Even if it's there, it's not a big deal. Let me turn off the mask and the outline so it looks as if this is exactly how it should look on your screen. All right, so once we got this, the goal is to figure out what is the pixel size of our nuclei, right? So you would hit calibrate right away. So I'm calibrating it. And it's going to tell me the right diameter, which I need by default. And it's going to give you the spinning wheel of death, but don't worry, it should be fine. Okay, so it's telling me roughly 62 pixels is the right number. Once it does that, if you want to segment cytoplasm, you say cyto, or if you want to segment nuclei, say nuclei. So I want to segment cytoplasm right now. The channel I want to segment is green, and the nuclei channel is red. So I'll say red over there, and I'll go ahead and hit run segmentation. All right, once I hit run segmentation, it's going to give me something like this. Now, this is something which is tunable. If you want, let's say, fewer cells, just the way we did with StarDist, you can tweak the model match threshold. So if you go towards left, you get most of the cells selected, sometimes more than you want. So try to find the sweet spot. Cell probability threshold. If you want more of your ROI to be fitting the cell, you should go towards left. But if you want less of an ROI fitting your cell, you should move towards right? So you can see how this is changing as I go from left to right. And once you are happy with this, you can do a few things, but I know that what I'm looking, let's say right over here, let me annotate this real quick to show that to you what I'm talking about. So you can see right over here, I don't want this. This is not of my interest. I know that these two cells right over here, actually this one cell appears as two cells over here, right? I did not want to include some of the cells which are on the edges. So on Cellpose, you can annotate some of these regions and in fact remove some of them if you're not happy with that. So let me go ahead and clear my drawing so that we can go ahead and do this manually. So if you want to, and let me just pull up the slides over here, and I'm just going ahead of what my slides are telling me. All right, so you got this, we passed that stage. Now, what do all of these things mean? And some of the useful shortcuts is I want to draw something, right? So I can right click and release, that's gonna draw an ROI. And if you can hit control and left click, you can delete an ROI or a drawn object, okay? So that's what I'm gonna do. I'm going to, let's say, remove some of this object. So control and left. So I'm using Mac, it's command and left click on my Mac. I think on PC, it's control and left click. So if you are using Mac, it's command and left click. But if you're using a PC, it's control and left click, okay? So let's say this is one cell. So I removed that ROI. I know that this is not of my interest. I want to remove this. So it's command and left click. I removed it, removed this ROIs. All right. Now, if I want to draw something, I can go ahead and if you, let's say, want to zoom into this, you can press 1 and you go into that quadrant. So this lets you go into different quadrants within your image. You can scroll back and forth to zoom in and zoom out. That also works, okay? So let's say I want to still remove some of this and I want to draw an ROI simply around this. So I right clicked and I'm just drawing an ROI around my cell. Okay, so I'm happy with that and that's good. Now, one thing, you see all these options over here, which says send manual segmentation to server. If you were to load Cellpose using Python, there are different ways you can send your segmentations to folks at Cellpose so that they can incorporate any kind of new cellular features to the models such that the whole community can benefit from. But because we are using this standalone GUI-based or executable file, we cannot do anything like that over here. The other thing that Cellpose recommends is when you are doing any kind of annotation, you do not use a combination of partially segmented using their software and partially manual segmented. They want segmentation from scratch, okay? So that's something to keep in mind. If you launch Cellpose using Python, there is a way to manually segment and send this annotated features to their server. Okay, so let's say we are happy with what we have. What is the next step that you do such that we can import this onto Fiji? So there are different things you want to do. One is save the masks and image as .npy file. What this will do is it will create this files, which is ._sag.npy, which means the next time you drag and drop this file onto Cellpose, you will automatically see all these segmented features or the masks onto your image, which is what exactly how it opens since I had done that already. You also want to, so let me go back. Okay, file. You also want to save this as save outlines as text for ImageJ. And this is how you can figure out all the ROIs around the image. Okay, so 1 and 2, and that should be it. And if you want to look a bit more fancy, you can also save the mask as PNG. So essentially there are 3 options: save masks and image, which is what you have to do; save outlines, which is what you have to do. And this is just in case if you want to look fancy, I'll show the last thing to you. Okay, so I've saved this already. So if you guys want to play with this, I'll let you go and give you like 10 minutes to play with this. And while you are playing with it, if you have any questions, let me know. If your Cellpose is loading, you should not have any problems. If your Cellpose is not loading, just contact me. I'll be much more happy to get you on one of our workstations and you can play with that. Okay, so I'll give you like 10 minutes to play with this. But if you are done playing with it before that, let me know. We can move to the next step. How do you all feel about this so far? Is it working for you, not working for you? Any thoughts as to how things are progressing? Happy to hear, even if it's bad, totally fine. Yes, I'll give you like probably 1 more minute and then move to the next step of this exercise. Okay, so moving to the next step of this process, which is we got all these ROIs. What do we do with them? How is it that we overlay this ROIs onto the cells using Fiji, right? So you probably saved, if things work for you the right way, you have saved this data sets. You have a .txt file in your folder, and typically the file should be in the same folder where you open the image from. Apart from that, I also gave to you these two files, one which is image_ROI_converter.py file, and I've also placed a Jython.jar file in the same folder. Okay, so the first thing that you will do is open Fiji and run a macro, which is plugins, macros, and run. It will open up a window. You will redirect towards this folder and click on image_ROI_converter.py. And when you try to click open the first time, what will happen is it won't go through. It will try to install Jython.jar file, and it will ask you to quit Fiji and restart, because this operation depends on the presence of the Jython program in it, okay? Or the Jython script rather in it, all right? So we'll do this step because I already have used Fiji and installed Jython once. My Fiji won't ask me to quit, but yours will. So let's repeat this process over here. What's gonna happen is you go to plugins, macros, run, and direct to the folder which says Fiji files for Cellpose, and click on this, okay? So, well, it does tell me, so that's okay. So I'm gonna say okay. It's gonna do the Jython thing, and it's gonna ask me to restart Fiji. I'm gonna say okay, which is great because we are all on the same page now. All right. Go back, reopen Fiji. Plugins, macros, run. Go back to my ImageJ ROI file. And this time it says it's starting Jython, right? And now it tells me where is my file. So now I want to show the path towards the text file, which is where my ROIs are stored. Okay, so I'm gonna go ahead and tell Fiji to go ahead and click on the outlines.txt file. And once I hit open, it's going to, oh, come on. Okay, it did not like that. I did not have any image open. So let me go ahead and open one of my images. So, all right, I have my image open. I'll repeat the same process, plugins, macros, run. The Python file, open that. And now redirect it to the .txt file. Okay, so two steps. One is first time open the Python file, .py file. Second time open the txt file. So txt file, and boom, it gives me all this ROIs, right? And we can repeat the same step that we repeated earlier. Now, again, over here too, you have the flexibility of deleting some of the ROIs if you don't like them. Because I did not resave, I told you I'm deleting few things, but I did not save it. That's why it's showing some of the cells. But I have the flexibility of deleting some of the ROIs here in the ROI manager if I'm not happy with that. So I can delete this. I can also delete this one. Okay, and that's pretty much it, right? So once I'm here, I can select my ROIs and do the same thing which I did earlier, which is Command N, open up a new window. This is 847 by 827. Open this up and go to more and say fill. So I get my cells, right? And this is something which we'll be using next time for Cellpose. And it's okay if you haven't saved, I'll provide you with files with proper names for the next Cellpose session, okay? But the point is, we want to automate something that is generated from deep learning models, the mask which we generate from deep learning models. And even here, based on this mask that you have, if you, let's say, simply want to, and let's make sure we are in the right image. Right now, I'm in the nuclear image, but if I go back to my cytoplasm image, come on, it doesn't like that. So I'll duplicate my second image and keep it over there. Not want to. Certainly is fighting with me. So let me just close this, reopen, uncheck the labels, reopen my image, and I only want the second image. Come on. Okay. Now, if I want to get all the information in this image, which is what is the area of individual cell, what is the mean intensity for each of the cell, I can easily do that. Just go and measure, and I get all the property, right? Which is what is the area, perimeter, integrated density, mean intensity for each of the cell. And this is something which, let's say, if you are doing cell motility, migration, if you are working with cell death, if you are doing time course measurements and you want to see what's happening with your cell over the time, this can be very helpful. And you can get data from hundreds of cells, which can make your data set look nice. It will look good on your paper and so on, right? So it's that easy. The reason for creating mask again is to use this next week for cell profilers. So even if you don't generate that, that's okay. I will provide you with masks in a folder for next week. Okay, so that's all I wanted to show you. Take your time, try to see if you can replicate this, and if you have questions while you're doing this, let me know. And again, a point that I want to make is compared to last time where we did the whole thresholding based masking for the cell, which was very cumbersome, very painful. This is straightforward, less painful, gives you a ton of data instantly. And we haven't even trained a model. We are using a pre-trained model to generate these cells, okay? And I have also included one more data set that you can play with. So that is a tissue lever data set. This is courtesy of Dr. Nikita Gupta's lab, where the intensity of the cells is very, very dim compared to background. So if you want to play with one more data set to know how the Cellpose model works on this, feel free to play with it. This is just to include something which is not that great, but still Cellpose does a pretty good job even at outlining some of the cells. Okay, so this is something you can play with by yourself using Cellpose. Is this working out for you? Any issues, any troubles in the process? I would love to get your feedback. Just want to know if this is too cumbersome to get through getting some masks.
So I don't know why my Fiji keeps giving me reverting colors. So I can get the ROI okay, but it's just black outlines. So I can create a new image with white background and then everything works. But with the black background, I can't.
So the outlines of your ROI has black color. Is that what you are saying?
Yeah. So I try to create the new image, like what you show,
Right.
and it won't work because the ROIs are all black outlined. But if I do a white white
Right.
background, then it works.
So what you can do is, well, you can go to, trying to find my feature. Okay. You can go to Edit, Options, and for colors, not this one, Edit, Options, line colors. There is a tool for line colors which you need to select, and that should help you figure out how it should look like. So
Okay.
let me do this. So right now my foreground is white, background is black, and if I open a new image, let's say this. So even my lines are black, right? I really cannot see anything. Is it the same?
Yeah, this is what I had. Yeah.
Right. And I think it's okay. It's not a big deal, right? Because eventually you want to select all of this, shift click and go ahead and do more and fill. And it's gonna fill up all the ROIs for you.
Right. Okay.
Because that's all we care about anyways.
Yeah. Yeah.
Okay. And if you're wondering why we care about this right now, you can just save these files, but you will know that this is something which will be helpful to us next week. And if you remember from last time, you can do image math based off of this. So let's say if you have this, if you generate masks off of nuclei, you can do image math where you subtract the nuclei from this, and you only get region which is cytoplasm and not the whole cell. And these are the kind of things we will do next week.
Gotcha. Thanks.
Okay. Yeah, you're welcome. Any questions while you are doing this? Anybody else? Welcome, Vasanta. So if you're working with your data sets and if you have questions with any of this, feel free to reach out to us during the week. Totally fine with us. Then let's take about 5 more minutes and then we can try to wrap the session up. You're welcome.